Well, hello everyone, and welcome to lecture 2 on the Advanced Inorganic Chemistry course. I want to continue our discussions surrounding F-block elements today, and I want to start to think about trends in the metallic and ionic radii within the F-block. What happens to those metallic and ionic radii as we cross the F-block, as we move from left to right across the lanthanoid and the actinoid elements? And I want to look at a particular feature of this part of the periodic table, which is known as the lanthanoid and the actinoid contraction. I'd like to start thinking about explaining the trends in the ionization potentials as we cross the F-block. And I'd like to, particularly for the lanthanoids, relate those ionization potentials to a consideration of the available oxidation states in the F-block and what that means for some of the chemistries of the compounds that these elements form. And of course, that will become important as we proceed through the course and look in more depth at the chemistry that these elements exhibit. Now, if you look at the metallic radii for the lanthanoids, you will see that by and large, there is a general decrease in metallic radius as we go from lanthanum through to lutetium. So I show you on the right there the atomic number, starting at scandium, so in the transition series, then through lanthanum, and finally ending up on lutetium. As I said, the general trend is a decrease in metallic radii. Note that at the moment, I'm talking about metallic radii. So if you had a block of cerium on the table, that would be the radii that we're talking about, the metallic radii, not the ionic radii. So electron configuration still as you see it in the periodic table, the ground state electron configuration. You'll note then there are two maxima in that graph. There's one found at europium and another found at ytterbium, and they have distinctly larger metallic radii compared to the rest of the lanthanoids. And we can explain that quite simply by first considering the electronic configurations of the elements. And if you look back at the electron configurations from lecture 1, you will see that here europium and ytterbium have a half-filled and fully filled 4F subshell respectively. So there's an energetic benefit to them having a half-filled and full F shell. And we can relate that to the metallic radius by considering a very simple model of metallic bonding. So you'll remember our very simple model of metallic bonding as being metal cations, which are essentially islands of positive charge in a sea of delocalized electrons. Now, of course, that's a very simple representation of a much more complicated process. Really, of course, what's happening there is that metals are bonding through a delocalization of orbitals to form molecular orbitals. And mathematically, then, we treat the electrons as being delocalized over the entire metal. But here, this simple model works very well in explaining why that metallic radius increases at europium and ytterbium. Now, let's consider first the orbitals that are available here for delocalized metallic bonding. Remember, if you think back to lecture 1, when we were speaking about the radial distribution functions of the sort of 4F and 5F orbitals, we said that those 4F orbitals are very core orbitals and they don't really take part in bonding. If you look back at the radial distribution functions, you'll see that they sit quite close to the nucleus, they're core orbitals, and they don't like to get involved in bonding. So the only orbitals that europium and ytterbium have available for bonding are the 6s orbitals, in which they have 2 electrons apiece. So those 2 electrons within the 6s orbital are available for this delocalized metallic bonding. And we can therefore think of europium and ytterbium as Ln2 plus ions. I use the Ln there as the generic term for a lanthanoid. So we have Ln2 plus ions in a sea of delocalized bonding electrons, but those electrons only come from the valence orbitals here, the 6s orbital, because those 4f orbitals are too core and they don't want to get involved in bonding. Now, if you look at the metallic configurations, if you look at the electron configurations of all of the other lanthanoids, then all of the other metallic lanthanoids, then you'll see that they have 5d orbitals, and they have largely 1 electron in their 5d orbitals. Here then, there are 2 sets of valence orbitals, if you like, that are available for this metallic delocalized bonding. And in all of the rest of the lanthanoids, there are 3 electrons, 1 electron from the 5d orbital and 2 electrons from the 6s orbital, that are ready for this delocalized metallic bonding. So we can think of the rest of the lanthanoids as really Ln3 plus ions in a sea of delocalized electrons. That's the reason why europium and ytterbium have larger metallic radii, and it's due to the fact that they form these Ln2 plus ions. And of course, we can expect an Ln2 plus ion to have a larger radius than an Ln3 plus ion. An Ln2 plus ion has more electrons, but the same effective nuclear charge, the same pull from the nucleus. An Ln3 plus atom has less electrons and the same pull from the nucleus, but because it has less electrons, each electron feels a greater pull from the nucleus, and therefore the radius of the atom is smaller. Now, this is also reflected in, I want to focus on the melting point here. If you look at the plot there, the red line is the melting point, and you see distinct minimas. The lowest melting points on that graph come from, again, europium and ytterbium. And again, we can use a very simple model of metallic bonding to explain why they have lower melting points. Their metallic radii are larger. Therefore, in our simple model of metallic bonding, they sit farther apart, and they sit farther apart from the sea of delocalized electrons, and the bonds that hold the metal together are weaker. So that explains why europium and ytterbium have lower melting points. And you'll see that they're distinctly lower than the rest of any of their neighbouring trivalent lanthanoids, by 200 or 300 degrees Celsius in the case of europium, and by at least 600 or 700 degrees Celsius in the case of ytterbium. Now, for the actinoids, the metallic radii are much less regular, and you can see on the plot on the right there, the black line corresponds to the metallic radii. The rest of those radii shown there are for the ions. But focus for the minute on the black line. You can see there's a much less regular pattern as we increase atomic number, as we move from left to right across the actinoid elements. And actinium through to neptunium show this parabolic decrease in radius. And that's because in this early part of the actinoid series, the 5f orbitals contribute to metallic bonding. And you'll remember why that was from lecture 1. That's due to these relativistic effects and the fact that we actually get a slight expansion of the 5f orbitals due to these relativistic effects. They're happy to participate in bonding, and you see this broad decrease, broad average decrease in in metallic radii. However, as you get towards the right-hand side of the actinoid elements, those actinoid elements with higher atomic numbers, you see that those 5f orbitals actually become much more core-like, and they make less of a contribution to metallic bonding. But there's no real regular pattern to these. Now, what about ionic radii? Well, if you look at the ionic radii of the lanthanoids, and I show you here the ionic radii of Ln3+ ions, again from lanthanum right the way through to lutetium, you'll see that there's a very clear, steady, precise decrease in the ionic radius of the 3+ ions as you cross the group. And there's around about a 14% decrease in ionic radius as you proceed from lanthanum through to lutetium 3+. And exactly the same is true for the ionic radii of the actinoids. If you look at the red, green and blue lines on that graph, you'll see they correspond to the ionic radii for a 3+, 4+ and 5+ ion. Again, the decrease in the radius of ions here is very steady. Now, if you were to compare the metallic radius between the lanthanoids and the first, second and third row of the transition series, you see a very stark difference. Apart from those seemingly anomalous results at europium and ytterbium, the trend in the decrease of the metallic radius is pretty consistent. That's unlike that of the transition of the first, second and third row of the transition elements. And similarly, if we compare the ionic radius of the lanthanoids to the first row of the transition series, you get this double minima type graph in the first row of the transition series. And we can compare that to this very steady and precise decrease in the ionic radius of the lanthanoids. And this can be explained by considering something called the lanthanoid and actinoid contraction. It applies to both the lanthanoids and the actinoids. I'm going to focus here on the lanthanoids, but the same is true for the actinoids, and it goes some way to explaining why we get this very consistent, systematic decrease in ionic and metallic radii as you cross the group. The formal definition then is that there is a decrease in ionic radii from lanthanum 3+ to lutetium 3+ due to imperfect shielding of the 4f electrons from nuclear charge. And you can see I've shown that schematically there. Let's consider some of the electron configurations. Well, I show you some electron configurations for the 3+ ions now, because this is easiest to explain if we consider the 3+ ions. So you can see that as we cross the group, the only difference in electron configuration is the number of electrons in the 4f orbital as you cross the group. So cerium has 1 electron in its 4f orbital, and that decreases by 1 electron apiece until you get to lutetium, which has a full 4f subshell with 14 electrons. So you can see that as you cross the group, the only real thing that's changing is the occupancy of that 4f subshell. Now let's think about a simple model of the atoms involved here, and what what I would call frontier orbitals are involved. What outer orbitals are we talking about? Well, there's the valency shell, which is the 6s shell. There's what I would call the penultimate shell, so the one before the valency shell, which is a 5d shell. And then there's a 4f shell. And we can think about the distance between the nucleus and the valency shell as a measure of the attraction between electrons and the nucleus. As we cross this group, as we go from left to right across the lanthanoids, the only thing that's happening for these lanthanoid 3+ ions is that electrons are entering the 4f subshell. Now, as we move across the group, the proton number increases. We're adding protons as we move across the group, and therefore the effective nuclear charge increases. Right? The attraction that electrons feel to the nucleus increases as we increase proton number. And we can measure that with a very simple equation. The effective nuclear charge is equal to the atomic number, or the number of protons, or the pull that the nucleus has on those electrons, minus the shielding capacity of the orbitals and electrons that are between the nucleus and the outermost electrons. Now, those 4f orbitals are the orbitals really that are shielding the outermost electrons from the pull of the nucleus. And you'll remember that the 4f orbitals are very, very diffuse. They've got no node at the nucleus. They're an odd shape. And because they're diffuse and they don't have a node at the nucleus, they're very poor at shielding valence electrons from that increase in nuclear charge. So the shielding capacity is very low. And as you cross the lanthanoids, you increase the proton number, so you increase the pull of the nucleus on the outer electrons. And as a result of that, the lanthanoids show around about a 14% decrease in ionic radius, and the actinoids show around about a 13.4 decrease in ionic radius as you cross the group. Now, what you might say is, well, yeah, okay, that's fine, but surely, in the transition series, when we're crossing a group, the 3d or the 4d orbitals shield, and why don't we see such similar consistent trends in the transition series, the first rows of the transition series, like we see in the lanthanoids, and indeed the actinoids? And the result of that, or the reason as to why that is because it's not just a simple electrostatic effect that is causing this contraction. So we know that as we cross the periodic table, we are increasing proton number. Our 4f orbitals are poor at shielding. Therefore, as we increase the proton number, the effective nuclear charge increases and the metallic and ionic radii decrease. But there's another element at play here, and that's those relativistic effects that we were talking about in lecture 1. So if you need to recap on that, have a watch of lecture 1 again. There are two contributions then to this lanthanoid and actinoid contraction as you cross the group. And indeed, it's estimated that about 10 to 30% of the lanthanoid contraction and 40 to 50% of the actinoid contraction are due to these relativistic effects. So you can see the big impact then that these relativistic effects have on the metallic and the ionic radii of these elements. It's not just the fact that we're increasing proton number and increasing effective nuclear charge, and that these 4f and 5f orbitals are actually quite poor at shielding that increase in nuclear charge. There is another component at play here, and it's these relativistic effects. Okay, I would like us now to consider the ionization potentials and the oxidation states for the lanthanoids. So what I'm going to ask you to do is pause the video here And there is an exercise associated with this lecture on Moodle under the lecture 2 page. I'd like you to download the file and complete the exercise, and you'll need to open Microsoft Excel for this. And I'll go through some of the answers when you're ready. All you've got to do is hit play to continue. The point of this exercise is to get you to play around with some data which relates to the first, second, third and fourth ionization potential for the lanthanoids, and also to get you to draw some conclusions from that data. So I'll pause, well, you pause here and resume when you're ready. Okay, so you should have had a play around with that data and you should have plotted two things. Number one is the first 4 ionization potentials for the lanthanoids versus atomic number or element name. And you should have also plotted the sum of those first 4 ionization potentials versus atomic number. And I'll attempt to answer the questions that were on your exercise sheet. So the first thing that you notice from the ionization potentials is that the first and second ionization potentials are low, and they vary little along the series. They're all basically the same, right? The first ionization potential is around about 500 kilojoules per mole, and the second ionization potential is around about 1,000 kilojoules per mole. The third ionization potential then shows 2 distinct maxima, and surprise, surprise, we see them at europium and ytterbium once again. Well, that has been shown already in terms of metallic and ionic radii. Let's have a look at those in a little bit more detail. Europium then has an electron configuration of 4f7,6s2, and ytterbium has an electron configuration of 4f14 and 6s2. And we're looking at the third ionization potential here. So we're looking at how much energy is required to remove the third electron. And of course, if you were to move the third electron from each of those elements, you are trying to remove an electron from a half-filled 4f shell in the case of europium and a filled 4f shell in the case of ytterbium. So it's very difficult to do, and it requires more energy than the rest of the ionization potentials in that group. What it tells you then, I think I asked about the oxidation state, is that for europium and ytterbium, the +2 oxidation state is likely to dominate its chemistry because it requires more energy. In each case, it probably requires 400 or 500 extra kilojoules per mole of energy to remove the third electron. So it's just not energetically sensible for europium or ytterbium to exist in the +3 oxidation state. So they prefer to lie in the +2 oxidation state. Now, we can compare then the fourth ionization potential, and we'll compare that against the rest of them, the first, second and third ionization potential. And what you can see is that the fourth ionization potential is much higher than the first, second and third. And I think in all cases, it's actually higher than the first, second and third added together. So what it tells you is that fourth electron is very difficult to remove. It requires lots of energy to remove that fourth electron, and that the +3 oxidation state will largely dominate the chemistry of the lanthanoids. Of course, that's not the case for europium and ytterbium, where the +2 oxidation state dominates. But broadly, you find lanthanoids in the +3 oxidation state. Cerium is the only lanthanoid that exists in the +4 oxidation state in solution. If you were to remove the fourth electron from cerium, you are leaving behind a closed shell configuration because it only has the fourth electron is a 4F1 configuration. So if you remove that, you're leaving behind a closed shell configuration. So you do see cerium in the +4 oxidation state in solution. Now, if we look and compare that to the ionization potentials for the actinoids, you see the case is markedly different. Firstly, the experimental data are far less complete, and that's solely because people can't get enough of it for a long enough period of time to take any meaningful measurements. And you can see that not even the first ionization potentials are complete for all of the elements. There's 4 elements there for which we have to estimate the ionization potential for. Now, you'll remember that the electron configurations for the actinoids are a little bit irregular, particularly at the start of the group. And that's because the 5F and 6D orbitals are very similar in energy. So you get these quite irregular ground state electron configurations, and you can see that that's reflected in the early part, particularly from actinium through to plutonium. Broadly, the first ionization energy is very irregular, again, reflected in quite irregular electron configurations. However, the later actinoids, those electron configurations correspond far more to those of the lanthanoids, albeit this time we're filling the 5F orbitals. And you can see that there's a clear increase in the ionization potential as you cross the group until you get to lawrencium. And lawrencium's quite an interesting element because it has a measured first ionization potential that is significantly lower than the rest of the actinoids. Indeed, it's also lower than any of the lanthanoids. And researchers think that this is a result of those very strong relativistic effects. So it's been proposed that due to relativistic effects, the 7p orbital is stabilized relative to the 6d orbital, and that in fact the true electron configuration for lawrencium is one in which the outermost electron occupies the 7p orbital, and so the 6d orbital is not occupied, i.e. the 7p orbital is lower in energy than the 6d due to these relativistic effects, and that 7p orbital and the electron within that 7p orbital is very weakly bound. And as a result, that explains the very low first ionization potential for lawrencium. But it does raise questions as to where the appropriate place for lawrencium is in the periodic table. If you think about the transition elements, a true definition of the transition elements is to have partially filled D subshells. The F block would be defined by having partially filled F subshells. And if this is true, and this is a relatively recent study, and the outermost orbital for lawrencium is indeed a p orbital, then is it better placed in the p block of the periodic table? And indeed, you can compare ionization potentials, and because this 7p electron is so loosely held, it actually has oxidation chemistry, which is very similar to that of the first group of the periodic table. So those very reactive alkali metals that readily lose an electron. So it's a difficult one to place this, and I put some extra reading, or I put some directed reading in the folder on Moodle. So please have a look at that and decide for yourselves where you think lawrencium should sit in the periodic table. Okay, I would like to leave it there. Hopefully, you've managed to complete those exercises and draw some conclusions about the oxidation states and ionization potentials for these elements. We've shown that across the lanthanoids and actinoids, the metallic and ionic radii decrease with increasing atomic number, and that these effects aren't just due to those electrostatic effects in terms of shielding, but are also due to some relativistic effects that occur as electrons move in orbitals, and that we can use those ionization potentials that you looked at in the exercise to predict some of the available oxidation states for these elements and their compounds. And I will leave it there. Thank you very much.